Okay, let's get started. Only 5 of us? Okay, what happened? The lecture remote on Tuesday. All right, okay, but after all, the snow is down, right? Hopefully that was the last snow in this spring. We got too much snow, breaking records. Okay, so let us continue with the Gibbs sampling. So in the last lecture, we talked about Gibbs sampling, right? So it was motivated by the random walk behavior. If you use just like ordinary Metropolis Hastings sampling, you use symmetric distribution to generate proposals, then it's very likely that your generated proposal will be rejected, right? Why? Because you want to find out, you want to generate proposals which happen to sit in the high density region of your target posterior, but actually you have no idea where the high density region is, right? If you just blindly use some symmetrical proposal, that's basically saying like you're just blindly generate proposal, right? It's very likely that you didn't hit the high density regions, then it's very likely you got rejected. And this is gonna reject it. It's gonna waste a lot of computational resources. That's why people don't like this because it is costly, it is inefficient. Right? So one way of addressing this problem is using Gibbs sampling, right? So just quick review. Like suppose you got your random variables, like m random variables in total. And we're assuming that given each random variable CZI, so given for each random variable ZI, given the remaining random variables, which we call Z not I, namely the Z variables that does not contain I, and given the data D, we assume this condition distribution is tractable and easy to generate samples. Then Gibbs sampling is just to cyclically generate new sample for every element in Z, conditional on all the other variable samples, and that's it. Right? So if you take a look at the algorithm framework, it's pretty straightforward. Right? For each step, right, you're gonna first condition on all the current examples from Z to N to ZMN. You use the condition distribution to generate the new sample for Z1, which we denote by Z1N plus 1, right? And then you condition on Z1N plus 1 and all the other samples of the remaining elements other than Z2, right? Like Z3N to ZMN, you use the condition distribution to generate one sample for a new sample for Z2. You got Z2 N plus 1, right? So similarly, you just condition on all the current examples of the elements in Z. Other than the target variable, you use the condition distribution to generate new elements, right? Until you're able to update every element sample in your random variable, right? Then you generate a new sample for your whole and the variable vector Z. Right? So just keep doing this, right? So we have shown that several one particular applications where Gibbs sampling is very convenient, like matrix factorization, right? So the K of the matrix factorization is that, okay, in the likelihood, we're assuming your rating for a particular movie by a particular user is a Gaussian likelihood where the mean is dot product or inner product between the representation of the user and the representation of the movie, right? And even you use Gaussian prior over user representation and over each movie representation, you find that you are not able to exactly compute the posterior. The reason is you multiply two Gaussian vectors together, it won't give you a Gaussian. You can try that. I've tried numerous times. It won't work. Right? But the good thing is that if you apply the Gibbs sampling, meaning that every time when I generate a sample of say UI, condition on all the other users representations, the movie's representations like VI and all you like you not I, something like this, right? So you see that because now the inner product where you contain UI, the representation of the movies are viewed as a fixed constant. Then if you look at this conditional distribution, you see that's just a multiplication of set of Gaussian, right? And exponent is just a linear transformation, a set of linear transformations of the user representations. You see that you merge them together, it will still be a Gaussian. So you can check it by deriving it by yourself. So that means if you use give something, you can immediately get the conditional distribution for every user's representation and every movie's representation conditional on all the other random variables are Gaussian, and it's very easy to generate new samples. So you can just do it cyclically to get new sample for every user and movie and so on. Okay, so after talking about the algorithm framework and also illustrating like in some cases it's really useful and convenient, next we're gonna justify why we can do so, right? Why give something is correct. So we previously discussed, right, to construct a valid Markov chain and to get posterior samples, right, we need to ensure that the target posterior is invariant to the transition kernel of your chain, right? So we would like to say if give something satisfy this condition, right? So one might think of like, okay, to show that, why not that we first show detail balance, right? If we show the transition kernel of keep sampling satisfy detail balance, and then we know that the target posterior will be invariant to the transition kernel, right? But here we're gonna use a even simpler proof to directly show the target posterior is invariant to the chain, namely that your chain will eventually converges to the true posterior, target posterior. How do we see that? So first, we need to know what is the transition kernel. So transition kernel, as the name suggests, right? Say at step n, I got my sample Zn, right? Transition kernel is just the conditional probability that you conditional Zn, you sample Zn plus 1, right? Suppose your Z random variable contains m elements. So to get a new sample of the whole Z vector, how many steps did we conduct in the keep sample? David. Yes, exactly right. Remember, in the keep sampling framework, every time we're gonna condition on the current samples of the remaining variables, just sample one variable, right? And if you want to get a brand new whole random variables vector, you're gonna go through every element, right? So you have to perform m steps here. M is the number of the elements in your random variable vector Z. Right? So that means we can write down our transition kernel as a multiplication of m conditional probabilities, right? So the first one is the conditional probability to sample Z1 n plus 1, conditional on all old variables in Z1, Zn, right? And then the second probability, second conditional probability is that is you're going to condition on Z1 n plus 1 and the Z3 n to Zmn to sample Z2 n plus 1, right? And just continue the product until the last one is that, okay, condition on all the new samples for Z1, Z2 to Zm minus 1, you sample the new sample for Zm, right? Which is Zm n plus 1. So we're going to show that your target posterior is invariant to this transition kernel, which is a product of the m conditional probabilities. Right? We're going to see this. By the way, any question regarding this? Okay, so when we claim that, okay, the target posterior is invariant to the chain, it just means that, okay, if you got your sample Zn really sampled from the target posterior. Then through your transition kernel, you generate new sample Zn plus 1. The distribution of this sample should also follow this true posterior, right? That is called invariant. Namely, that your distribution of your sample or state doesn't change, right? When you get a new sample, right? That's called invariant, right? So we're gonna see why this is true for the Gibbs sampling. So suppose at step n, I indeed get a random vector, which is sampled from the true posterior, right? So then we know that we're gonna generate a new state or example of Z, which is Zn plus 1, following these M steps, right? And through these M steps, we know that we actually have a M intermediate states, right? The first intermediate state is that, okay, I'm gonna get my new sample for Z1 and all samples for Z2 to Zm, right? Through this conditional distribution. And next intermediate state, that I'm gonna have a new sample for Z2 and combine with new sample for Z1, all sample from Z3 to Zm, right? Like you just continue to mix the new samples in Z and all samples in Z until at the last step, you got all samples for every element in your Z, right? That's our observation. If you conduct your Gibbs sampling. So we want to claim that each of this intermediate state, if the initial state Zn really comes from the posterior, each of this intermediate state will follow posterior as well. How can I see this? We just need to see one example. You'll see why this is true, right? So first, because Zn, we assume it is generated from the true posterior. So that means the marginal distribution of Z2n to Zmn, this guy follow the marginal distribution with Z1 marginalized out, right? Because this is a whole vector, right? This is a whole vector, Z1 n to Zmn, right? This whole vector is following the true posterior distribution, right? And now, of course, each subvector will follow the marginal posterior distribution with all the other variables marginalized out. So this basically means if we just take a look at Z2n to Zmn, right? They're gonna obey the marginal posterior where you have Z1 marginalized out, right? It is like Z2 equals to let me use a more succinct notation, like Z2 to M just equals to Z to Mn given theta D, right? Does it make sense? Okay. Okay, so now let us look at the first step, right? The first step is that I'm gonna condition Z2 to Zmn, meaning that I'm gonna assume that, okay, the second to the last element of Z will take those samples. Then we use the conditional distribution of Z1 to generate a new element for Z1, right? A new sample for Z1. In other words, let me write it in more explicitly. That means Z1 and plus 1 will be sampled from a conditional distribution of Z1 given Z2 to M, taken the samples at step n, right? So it's Z2 to M. And so here, this is just a succinct notation of Z2 and Z3 and to Zm, right? And given the data D. Does it make sense? This is actually tells you how the new sample for Z1 is generated. Right. So now, if we want to look at the joint distribution of this mixed sample, right? Z1 n plus 1 and Z2n to Zmn. How do we get our joint distribution? Right. We want to look at the joint distribution of Z1 n plus 1, this new sample, right? For Z1 only, and also the old samples. What's their joint distribution? Let me use Q a few to avoid confusion. Right? What is their joint distribution? Yeah, multiply them, right? I know that. Okay, Z2 to Mn is all samples from this marginal posterior, right? And then multiply the condition distribution of them, condition distribution of Z1 condition of them to generate Z1 n plus 1, right? If you want to look at the joint distribution of Z1 n plus 1 are those all samples, we will just multiply them together. So what is the result of their product? Like, this is like asking, what is multiplication of conditional probability of A given D times the conditional probability of B given A and given D? What's that? Yeah, that's it. Right? This is simply joint distribution A and B given D, right? This is same thing, right? Your conditional D, you're all conditional D. So that means this is just the joint distribution of Z1 equals to Z1 n plus 1 and Z2 to M equals to all samples given D, right? Right? It's just the rule, the product rule of the joint probability, right? So now we can see that actually the probability of this Z1 n plus 1 mixed with Z2n to Zmn, they follow the true posterior, right? Does it make sense? Right. So basically the probability density of Z1 plus 1 to Z1 plus 1 and all samples of Z2n to Zmn, their density exactly the same as your posterior probability where your Z1 to Zm takes those samples. So this basically means they follow the true posterior. So you can see that, okay, the first intermediate state, it actually respects the true posterior. And similarly, using exactly the same argument, you can show that the second intermediate state respects the true posterior. We continue until the last state, which is the new sample vector, brand new sample vector, Zn plus 1, will respect the true posterior spot. Does it make sense? Like, this is just a game, like using conditional probability multiplying with marginal probability. Okay, that's it. Any questions so far? Okay. So, so now we can see that Gibbs sampling is through the conditional sampling, like conditional generation, indeed generate ensure our chain converges to the target posterior we want. Right? But you need to be careful. That is the ergodicity. Right? So it is possible that if your conditional distribution does not well behave, it is possible that you can only generate samples in a small region. You cannot explore the whole sample space. So that means you can miss some part of your true posterior density. That's not something we want, right? So then how do we check if your keep sampling is ergodic? Like one sufficient condition is that if you find that none of the conditional distribution will be zero anywhere in the sample space, for example, if your conditional distribution is Gaussian distribution, we know that in a Gaussian distribution, at every value in the real axis, they're gonna have a non-zero density, right? So that means it guarantees that you have some non-zero chance to jump to every possible point in the real space. Then it will be ergodic. But if your conditional probability is kind of like restricted, like truncated Gaussian, right? Means it only generates samples in this region. It won't be able to generate samples here and here. Then you need to be careful, because it's possible that it forms a reducible chain that it's gonna only alternatingly generate samples in some subregion of the whole sample space. That's not what we want, right? And in that case, you need to explicitly prove the ergodicity. Any questions so far? There. Yeah, we need to prove two things, right? As we previously discussed. First, your chain really converges to the target posterior, or in other words, the target posterior is invariant to your transition kernel. Second thing, you need to show that it is ergodic. It basically means whichever initialization state distribution you choose, it will eventually converge to the same distribution. And to show the ergodic, there are a lot of methods. Like here, we just give one simple sufficient conditions. Like if your conditional distribution has no zero support, meaning that has no regions where you have a zero density values, that is sufficient. But if it is not, there are a lot of other conditions. If you have taken some ECE class before, they have like big class just talking about Markov chains. They talk about many cases in which cases you can show the chain is irreducible, in which case is reducible, and sometimes you have to calculate the return probabilities, namely that if you can jump back in 1 step, 2 steps, 3 steps onto infinite number of steps, if this total probability is bigger than 0, then probably can show the irreducibility, something like that. But anyway, in practice, it is not very often you're gonna need to show this ergodicity. Okay, so next we're going to talk about the connection between keep sampling and the Metropolis Hastings. So we will give another view of the Metropolis keep sampling. You will see that one iteration of keep sampling, meaning that you generate one sample of one element, actually conducts a Metropolis Hastings update. And you will see that because Metropolis Hastings just means you generate a proposal, then you test whether you're going to accept that proposal. Right? So you see that for the Metropolis, for the keep sampling, the acceptance probability is always 1. So you can have another view accordingly that this keep sampling is a very smart design of the transition kernel, which guarantees you with 1 acceptable probability. Okay. So to see that, right, let us just look at one step, right? We just consider sample the first element, right? The other elements, the case for the other elements are exactly the same. Right? So suppose this is my current state or current example, Zn, which you know we have the a sample for every element in Z, right? Which we denote them by Z1n, Z2n to Zmn. So to perform one step Gibbs sampling, that means we're going to condition the current samples for Z2 to Zm to generate a new sample for Z1, which we denote by Z1n plus 1, right? So then we get a new state, which we call an intermediate state, like several minutes ago, right? So we call it Z prime. Z prime consists of a new example of Z1 and all examples for Z2 to Zm. So let's see how much likelihood likely we're going to accept this proposal. So remember, we use the conditional probability. We use the conditional probability distribution to Z to n to Zm equals to Zmn and given data D, right? So this actually is our proposal distribution. Right? We use this conditional distribution to generate a proposal. Then in the Metropolis-Hastings framework, we want to say, okay, given this proposal, how much probability we're going to accept this proposal, right? So then we need to compute the acceptance of probability in the Metropolis-Hastings framework, right? We know that it is a minimum of 1 and a fraction, right? This fraction is, you're going to use your proposal, right, to evaluate the joint distribution of your model and data, right? And multiply with the proposal distribution that you start from Z prime to sample Zn, right? If you can remember, right? So in general, the acceptance rate is a fraction 1 and fraction from the proposal evaluated on the joint distribution, multiplying the proposal probability that condition on Z prime, you generate Zn, and divided by Zn evaluated on the joint distribution, multiplying with the proposal probability that given Zn, you generate Z prime, right? This is in general, like if we starting from Zn, you generate the proposal Z prime, what is the acceptance probability, right? So here, we just evaluate Z prime, like in a numerator, and then we need to compute the proposal probability that you conditional Z prime, you generate Zn. So according to the rule of the Gibbs sampling, this guy is also a conditional distribution, right? It is conditional again on Z2n to Zmn on all samples, but now you're going to generate a new sample as Z1, right? But here, new sample corresponds to this guy, right? Because you're starting from Z prime to generate Zn. So there's only one element where it's generated, which is this Z1, right? So now we know that this proposal probability is just a P of Z1n condition on Z2n to Zmn and condition on data D. Right? And similarly, in the denominator, you're going to first evaluate the joint distribution of your model evaluated at Zn, right? And then what is the proposal probability that you have Zn, you generate Z prime, which is simply the conditional distribution that condition on Z2 and to Zmn, you generate Z1 sample, Z1 n plus 1. Right? And then let us look at what this fraction is, right? So it is not it's not hard to say that why not we first divide on both sides, right? On both numerator and denominator by this marginal distribution of Z2 n to zmn and given d, right? Because it looks like it can give us something, right? So we divided on both numerator and denominator. So you can see that the first joint probability, the second joint probability now becomes the conditional probability of z1 n plus 1, conditional z2n to zmn and d. And in the denominator is conditional probability z1n, conditional z2n to zmn. Right. And now you can see that, okay, this guy and this guy is actually the same, and this guy and this is actually the same. The fraction actually is exactly 1. So we got the acceptance probability 1. So that's the benefit. So that's how that's where we can see the smartness of the Gibson. From entropy history, we will like it constructs very very smart transition kernel such that your acceptance probability is guaranteed to be 1. Again, I suggest you guys to tackle this yourself and to have a better sense of how smart it is. Okay, so last thing we want to talk about is about this problem. Okay? So although give something won't reject samples, that acceptance rate is 1, so effective avoid random walk behavior, but it doesn't mean it addresses every problem. It has a severe issue. It's called inefficient exploration. Why is it has this problem? Because those random variables could be strongly correlated. Then you do the conditional sampling. These strong correlations might restrict your new sample to be very near around the existing samples. That means you won't go too far, right? So you can imagine that you might quickly generate a lot of samples, but those samples are just surrounding the initial samples you get. It's very, very slow to explore to a larger space. And that means it will make your recovery of the whole posterior density much harder. Right? Any questions so far? Okay. So I will finish the introduction of Gibbs sampling. And next, sampling method worth discussion is called hybrid Monte Carlo. Why would we pick up hybrid Monte Carlo for the specific discussion? So far we discussed the Mitropoli Hastings algorithm, and the easiest way to implement that is to introduce symmetric proposal. That is the conditional. Let's just use a Gaussian proposal. Like say you got Zn, you want to generate proposal for Zn plus 1, you may just construct a Gaussian distribution, which with the current sample as mean, you set some variance, right? But that will bring random walk behavior because it's just blindly generate new samples around with equal chance around any direction, but it kind of miss. It has very large chance to miss the high density regions. That means most of your trials will just be rejected. Like, with a lot of examples, it will be very inefficient, right? And although the Gibbs sampling can well address random walk behavior, but the strong correlations between the random variables, right, make the conditional distribution sampling to be inefficient in that your new sample cannot go very far away from the existing samples. So that means your exploration speed is very, very slow. Right? So then the question is that can we address both problems? Right? Can we effectively avoid random walk behavior, but we're still able to very efficiently explore the sample space? The more efficient we explore sample space, the more likely we can quickly recover the posterior density, right? So like, suppose your posterior density is something like this, right? Suppose your posterior sampling is density is like this, right? If you can effectively avoid random walk behavior, that means every time you generate the sample, it might be accepted, like with high probability. At the same time, if we can quickly explore the sample space. That means you can jump here, jump here, jump here. You generate samples cover all the regions, right? So it can help you quickly recover the histogram of the whole dense region, right? If you're doing deep sampling with high correlations between the random variables, you might just generate a lot of samples surrounding here, right? It's very, very slow to come here and come here, or come farther away, right? Then the question is, how can we address these two problems simultaneously? Here we're going to introduce the so-called hybrid Monte Carlo sampling. Right? What is hybrid Monte Carlo sampling? This is also called Hamiltonian Monte Carlo. Right? You see that it's an augmented approach. So we're going to augment an additional random variable into a probabilistic model, but it has some physics interpretation. You see that it corresponds to some momentum variable in a physics system. Right? They actually turn the probability to the energy of the physics system. Right? They try to construct a physics system in a high-dimensional space where you assign some type of energy, like position energy, as the block drawing probability of model. Right? Then we're going to introduce some augmented random variable to initialize the momentum variable in the system. And then you're going to evolve that system. The evolution of the system will give you new proposal. And also to guarantee that this new proposal has very, very large chance to be accepted. In fact, if your system is ideal and you're able to exactly compute the evolution system, your acceptance probability is always 1. We'll see it's not possible in practice. You always have some error. So it uses the evolution of the physics system usually described by a set of partial ordinary differential equations, right? And theoretically, it can explore the sample space more efficiently. At the same time, with acceptance probability 1. Remember, if you keep sampling, you although have a acceptance probability 1, but it is very inefficient to explore sample space. I will say that practically, because you are not able to exactly simulate that physics system, so it will practically limited by the numerical integration error. This is the very general description about how this Hamiltonian system, Hamiltonian Monte Carlo sampling works. Right? So now we're going to talk about details. So first, we're going to introduce a simple physics system. I believe everyone has heard them before in high school. Right? At least in my high school, I have heard of it. So this system is like this. We consider a small ball in a m-dimensional space, right? And of course, like the most intuitive instance will be just 3-dimensional space, but that doesn't matter, right? Let's just assume, okay, there's an m-dimensional space, right? And you have a ball, and then you put the ball, put a small ball into some curve like this, right? Maybe it's a big ball, right? So if we give this small ball some kind of energy, right? We give some initial position, we give some momentum. Then want to look at how does this ball move in this system? Right? How does this ball move? Just give me a guess. Yeah, it's just the floating, right? It's just move along the edge of this big ball, right? Big ball. If you look at this ball, right? So just move here and then and reach another high position and go down and here and here and here and oscillate, right? Right. So now I want to ask, if this is an ideal system, meaning that there's no friction. There's no friction here, right? what will happen? It just keep oscillating, right? Another similar physical system is called pendulum, right? It's called pendulum, right? Okay, we're going to first look at the property of this Hamiltonian system, right? So we want to characterize how this system evolves. To this end, right, we want to identify the state of this small ball, right? So the state consists of two items. One is the position of the ball, and one is the momentum of this ball. Because it's an m-dimensional space, right? So your position should be represented by an m-dimensional vector, and your momentum, which is just the mass multiplying with the velocity, so it should be an m-dimensional vector as well. Right? So we can represent the position vector at time t by zt, and the momentum vector at time t by rt. Does it make sense? And then we know that associated with the position is potential energy, right? Which we denoted by U, right? So the potential energy essentially is a function of the position vector. So it's U zt, right? And associated with the momentum is the kinetic energy, right? Which we denote by K. So it's also a function of the momentum, RT. Then the total energy of the ball is the summation of the potential energy and the kinetic energy. You can view it as a function of both the position and the momentum. Right? That's the basic characteristics of this Hamiltonian system. So next, I'm going to introduce the rule which governs this Hamiltonian system. Right? So starting from any initial position and momentum like Z0 and R0, then the evolution of the system, namely how the position and momentum varies along with time t, can be described by this set of ODEs, ordinary differential equations. Right? So basically it tells that, okay, for every element of your position vector, see ith element, Zi, right? So the time derivative, namely the change rate of ith position or coordinate, is the partial derivative of your total energy with respect to the partial derivative of the ith momentum. On the other hand, the change rate of every momentum element, like say Ri, it is negative partial derivative of total energy with respect to the partial derivative of the corresponding position Zi. So don't ask me how this is derived. This is called Hamiltonian mechanics. Right? You can take some college physics, because they will tell you a bit of this, right? It's a little bit different, at least on the surface. It seems different from Newton mechanics, but they're essentially equivalent. So let's just keep this in our mind. This is just some physics law. Like, we don't need to worry why to ask why this is correct. It is fundamental physics law. It is totally equivalent to Newton's law. Everyone knows, right? So now we know some basics about this Hamiltonian system. And how do we associate our probabilistic model with this Hamiltonian system? Remember, our strategy is that, okay, I'm gonna use this Hamiltonian system to generate new samples or new proposals for my probabilistic model. Later, we're going to discuss why using Hamiltonian system is better. So how do we associate our probabilistic model to this Hamiltonian system, right? We can define the random variable in our probabilistic model as the position vector in your Hamiltonian system. Then we can define our potential energy as the negative logarithm of the joint probability. So you can define any function as your potential energy and kinetic energy, as long as you satisfy this rule. It is a valid physical system. Okay? So, and to construct a Hamiltonian system, we also need the momentum vector, right? So then we're going to introduce another random variable R. We define the kinetic energy as the quadratic function of R. And here M is a positive definite matrix, right? And in practice, people often use identity matrix or some diagonal matrix. But again, you are not restricted to this quadratic form. You can use whatever form you feel comfortable. Right? But I just want to tell you that is the often used kinetic energy is just this quadratic form. And then because we introduced two random variables, right? One is Z, which is from our original probabilistic model. The other is actually the momentum variable is coming from another independent distribution, right? So that means we essentially introduce additional random variable R, right? We can construct their joint probability. What's their joint probability? R and Z are independent, right? So the joint probability is simply P of Z, the joint probability of data and Z and D, and also the probability of R, right? The probability of R essentially is just the exponential of the proportional to the exponential of the kinetic energy, which is Gaussian, right? It's just R0 and M here, right? If you just take negative logarithm, they'll give you this. So you can see that actually, if you write down the total energy, which is negative log joint probability plus this guy, right? This quadratic function R, right? You see that their joint probability essentially is proportional to the exponential of negative total energy, right? If you take negative log total energy, this is just logarithm of the joint probability plus logarithm of your Gaussian distribution over the momentum variable R, right? And you take exponential, they just cancel, right? They give you the joint probability. Right? So actually, in this way, we construct a Hamiltonian system for our probabilistic model, right? The position vector corresponds to the random variable in our probabilistic model, right? And the kinetic variable is some additional independent random variable, which comes from a Gaussian thing. And then the joint distribution of Z and R is actually proportional to the exponential of negative total energy of this system. So, and then we're gonna work on this, we're gonna focus on this newly constructed Hamiltonian system and see how can we leverage the system to generate new proposals for Z. So here, just to review, like if we apply the rules of Hamiltonian system and say how does the position vector and the momentum vector evolves along with time, what will happen, right? So this is our potential energy, which is negative log joint probability. This kinetic energy is quadratic function of R. So this is a total energy, summation of the potential energy and kinetic energy, right? So here is just the copy the ODE that governs the evolution of the Hamiltonian system, we see that the change rate of the position, each position Zi, is actually, you just take the derivative. So this is partial H or partial R, right? And you take the element I, which give you this M inverse R, and take the ith element. Right? And this one is very interesting. If I want to look at where and how our momentum elements will evolve, right? According to the Hamiltonian systems rule, it is partial H or partial U, right? So if you just substitute all this into compute, you see that this is essentially negative potential energy, partial potential energy over partial Zi, right? And we know that the partial potential energy is negative log likelihood. So this guys just tell you the change of the change rate of the momentum is partial log joint probability of our original model over S element of Z. So a key observation here is that, okay, now you can see you evolve this Hamiltonian system, you need to use the gradient of your log joint probability, right? So you can see that it leverages some gradient information. It's not blindly evolve. That actually reflects why using this Hamiltonian systems evolution to help your general proposals will increase the acceptance rate, right? So it is not blindly generating proposals. It follows the route that kind of increase the likelihood or joint probability of your model. Okay, so now, given this Hamiltonian system constructed from our original probabilistic model, right? The key idea of HMC, Hamiltonian Monte-Carlo sampling, is that at every step, we're going to use the current sample Zn and a random sample of the momentum variable R as the initial state of this Hamiltonian system. And then we evolve this system to a particular time point t. Then we just pick up Zt as the proposal. Then test whether to accept this Zt as my new sample. That's it. So you can see that this is essentially a simulation procedure to generate a new proposal, right? So how do we simulate? We're going to simulate Hamiltonian system, right? Starting from, suppose currently I got my sample at step n is Zn, right? So I'm going to initialize my system with Zn and another random variable R is just a random sample from a Gaussian distribution, right? And then that means I have a given initial position and initial velocity to this ball, right? I'm going to evolve this system, evolve to a particular time t, and t is something you choose. And you just read out what's the position of your ball here. Then we use that as my proposal of Z. Then I just conduct some neutral pasting test to decide whether I'm going to accept this new proposal as my next example. So that's the framework. Any questions so far? David. What do you mean by large momentum? Yeah, I think you're hitting a critical point. And I know your meaning, but let me express it in a more rigorous way. So basically, what David said is that there's a little bit concern here. The proposal is actually not randomly generating. is generated deterministically. Like for a Hamiltonian system, like non-friction, you give me some initial state. After a certain time of period, there's no randomness. You just as this particular time ZT is fixed, is certain. Right? So, but how do you guarantee that you're gonna have enough randomness because we're generating random samples, right? So randomness comes from R. Comes from the momentum random variable, and that's why the run you have some you must have some distribution over R, which can cover the whole region. I wouldn't say it's a large momentum, but I say it's enough random momentum that ensure that you are able to generate R as any point in the sample space. It still relates to the ergodicity issue. It means that as long as your R is able to reach any point in the sample space, meaning that any point in the sample space has non-zero probability in your distribution of R, and then under mild conditions that your evolution to generate ZN proposals they are ergodic as well, meaning that they are able to cover every point in the sample space. So here's something a little bit different. That it was generated deterministic. So randomness is then brought by R. Any other question? Okay. So now we want to answer the question why doing this is correct. Right? Why you use a Hamiltonian system to evolve and then pick up the position at any time t as your proposal, it will give you, and then do the metropolisting test that you guarantee you're gonna find out, you're gonna converge to your true posterior. Right? So to answer these questions, we need to look at several properties of Hamiltonian system, and actually they are critical to show the correctness of the such sampling scheme. Right? So first property is called the reversibility. So basically it says, okay, if you start from some time t, right? And your state is 18 RT, and then you evolve your system to a certain amount of time s, you get your state z t plus 1 plus s and RT plus s. Then you negate their momentum, like to be negative RT plus s. And then if you evolve your system, like initialize your state in this way, meaning that you have the same position, but you reverse the direction of velocity. Then you evolve for the same amount of time. And then you see S, right? And then you negate the momentum again. You're going to recover the original state. This is called a reversibility. So why is this? Before we get into this in detail, right? Why is it important to talk about that? So remember, we want to show our sampling is correct, right? We might use detailed balance. Right? If we use detailed balance, we need to show that the joint probability that you start from Z, sample Z, right? Suppose Z is sample from your target posterior, and then multiply the joint probability you sample from Z to Z prime. This joint probability is the same as suppose you sample Z prime from your target posterior, and then from Z prime you sample back to Z, right? So the jumping from probability is the same as jumping back probability. Right? If you want to satisfy the detailed balance, this is the definition of detailed balance. So that's very important. That's where we can see important here, right? If your system cannot guarantee, it can reverse, right? It can go back. Then this guy, that means okay, if you start from Z prime, it might never be able to go back to Z. Then this guy will be zero. Right? You won't have this D2 balance satisfied. Does it make sense? Like you have to, and by the way, this is a deterministic procedure, right? And this is actually a delta function, right? So start from z, you got z prime given z, right? There's only one root, right? Through an amount of time s, you're gonna arrive at z prime, z prime, yeah. And then you need to guarantee that okay, from z prime you are able to get back, right? Otherwise, if this guy is 0, then you know this won't be an equality. That's why when we say when we evolve this system, right, we actually have 2 steps to construct the proposal. First, we're going to evolve following the Hamiltonian dynamics rules, and then we're going to negate the momentum. Then we'll arrive at the proposal. So from ZT, RT, we go to our proposal will be ZT plus S and RT plus S and negative. This is our state. Then we can show that, okay, if your ZT RT follows some target posterior, and then multiply the probability that ZT RT, condition on ZT RT, you go to this state, is the same as you suppose your ZT as your ZT plus S or negative RT plus S sample from the target posterior. Then from here, condition on this probability, you go to here. This is a determinist procedure. If you cannot guarantee from this state, you can go back to this. Then this probability or transition current is simply 0. That won't satisfy D2 bias. That's why it's important. Any question?
Using the system, how do we decide the direction of momentum?
You don't decide the direction of momentum. You just negate it. Like this is your ball, right? Your momentum is given by some random something, like R, right? R is sample from Gaussian distribution, right? You just random give some initial momentum that contains the direction. Right? Remember, it contains both direction and also the strength, right? And then you just evolve it. Like, say you can pick up some time duration, right? CS, right? So when you arrive here, right? Because we want to ensure that you pick up a state that you can go back to the original state, to the here, right? So that means, so here this is where the direction of your momentum, right? If you do not negate it, like if you keep this ball to evolve, right? It won't go back here, right? It'll go back to another side. They go back to another side, right? So if you want the system to go back, you have to negate the momentum, right? And then you know that if you're starting from here, you just evolve and same amount of time to eventually return to the original position, right? But you know, this is your current momentum, right? But at original place, this is where the original momentum, right? So that's why you have to negate this again to completely recover the original state. Does it make sense? Like, and you can also show this in the equation. I mean, algebraic to show that. I'm not going to show that. It's pretty easy, but I just want everyone to have an intuition why ensure the reversibility is important, because you need to use them to show the D2 balance. If you cannot show that, okay, starting from the new state, you can now go back to the original state, then your detail balance breaks. And second, how to do this, right? Just evolving Hamiltonian system won't be enough, because if you evolve here, right, if you do not change the direction, right, it will just keep going, right? It won't go back. Any questions so far? Okay, so so the next property of the Hamiltonian system is called conservation, energy conservation. So basically, it means your total energy doesn't change in the ideal system. So you can show this by looking at the rule, right? So dH over dt is equal to d partial h over partial u times partial u or sorry, it's not partial u, du over dt plus partial h over partial kinetic energy times dk over dt, and they will give you exactly 0. Right? So, so that's a very nice property, and actually, the energy conservation will guarantee you have a acceptance probability 1. And third property is called the volume preservation. So what does it mean? It means for any amount of time of evolution, the determinant of the Jacobian is always 1. What does it mean? Like, we know that Z and R, sorry, it's not 0. We know that the U, the potential energy and kinetic energy, sorry, Z, here is Z, right? So the position vector and the momentum vector, they're random variables, right? So although you initialize them and then you evolve them, although this evolution is deterministic, but you can view like at any time t, right? Z t plus s, R t plus s, right? They can be viewed as transformation of the initial state Z0 and R0, right? Z0 and R0 are random variables. So at any state, Z and R are random variables as well. Right? Because it's function of a random variable still a random variable, right? It just tells you that if you compute the Jacobian of the state at any time with respect to the state of any previous time, the determinant of this Jacobian is 1. And why is this useful? Remember when we talk about the random variable transformation, right? If you got a random variable x, you transform to random variable y, see y might be 2x plus 1, right? You want to know what is the change of the probability distribution over y, right? There is some formula we discussed before, right? We know that px dx equals to py dy, right? So it can give you that the density of y is basically the density of x divided by not using divided. I mean, I'm using divided by Jacobian. I mean, it's dy or dx, the determinant Jacobian, and also absolute value. So you want to know the transformation, the density of the transform random variable. You need to know the Jacobian of those variables, right, after the transformation, right? And here, but Hamiltonian system has a very nice property that this Jacobian is 1, meaning that actually even you evolve you transform your random variables, actually the probability density doesn't change, right? Any questions so far? Everyone's good? Okay, so now let us look at the general theorem. This theorem actually is not only applicable to the Hamiltonian system. It applies to any dynamic system. For example, we can use the Lagrange system or any other systems. It tells you that in the same scenario, if you want to use some deterministic dynamic system through its evolution to generate new proposal for your probabilistic model, how can you do that? And in which case it is valid. So we consider an arbitrary dynamics psi t, right? Psi t means that we're gonna starting from initial state at t is equals to 0 and evolve it until time t, right? And we denote v as the extended variable, as similar to the Hamiltonian system example. Z is the random variable in our original probabilistic model, but we also introduce a momentum vector as an augmented random variable, right? So suppose this dynamic system is initialized with v, right? And after time t, a certain amount of time t's evolutions through the dynamic system psi, I got my new state v prime, right? If the following conditions are satisfied, then we claim that this particular distribution P of V is stationary distribution of the Markov chain generated by this psi t and acceptance test. Okay. So of course, PT will be P of V will involve in this testing conditions. Again, this is in the whole framework. This is essentially talking about if I use a dynamic system to construct a Markov chain, right? Every time I'm gonna first randomly sample R, I denote by Rn, and then I pair with my current sample of Z, which is Zn. Then I throw my dynamic system psi, right, and evolve it for a certain amount of time t. Right? I got my new proposal Z and R, which we call it V prime, right? And then throw some test, then I got my Zn plus 1, right? It form one step of my Markov chain sampling, right? If you just keep sampling this, and if this procedure we just discussed satisfy these conditions, then we claim that your P of V is stationary distribution of Markov chain constructed. Does it make sense? Does this framework sounds comfortable to everyone? Okay, so then let us talk about what are the conditions we need, right, to ensure our dynamic system-based Markov chain is valid. So first, we want to introduce some operation R. And this dynamic system should be reversible under this operation R. So that means, it means that if I start from V prime, if I start from RV prime, meaning that, okay, I evolve V to V prime after time t, right? And then I apply R operation over V prime, then I use RV prime as my initial state. Then I evolve it again for the same amount of time t. Then I do the R again. Then we can exactly recover V. Does it make sense? It's like, okay, if I want to generate a proposal, I'm going to first start from current V, and then I got V prime, but it's not finished yet. We're going to apply an additional operation over V prime. R. So RV prime is the actual proposal. Right? And the reversible means that, okay, if I use my actual proposal as the initial state, and follow the same procedure to generate another proposal, it will be exactly V. Does it make sense? This is again, it's just to ensure the detail balance, because you want the probability you starting from the current proposal, a current sample to the next proposal is exactly the same as you starting from the sample proposal back to the original sample. David. Yeah, R in the Hamiltonian, just the negation of R. But of course, you're free to define whatever R you want, right? So this is just to sorry, it's just to ensure the reversibility, just to ensure the detail balance, meaning that okay, I'm gonna starting from this proposal and following the same procedure, exactly same procedure I generate the proposal, right? I'm gonna first evolve the system side with the same amount of time, maybe here is better, right? And then I apply operation R again, then I can recover this proposal. I can recover the original sample, right? Only in this way we can say, okay, they could satisfy detail balance, right? Otherwise, if you don't satisfy this, well, you're starting from any proposal, you are not able to come back, then there is not any detail balance, right? And second condition is that R is an involution. Basically means if you apply R to X and you apply R again, it will recover X. And for example, in the Hamiltonian system, we know that R is just negation of the momentum, right? If you negate momentum and negate it again, you just recover R. And third one is that I'm gonna use this acceptance test. So what's that? Given this sample RV prime, this proposal RV prime, right? I'm gonna accept it with probability minimum 1 and the ratio of the probability P over RV prime and the previous sample V, multiplying with the Jacobian, determinant of the Jacobian of the proposal with respect to the sample V. If you use this probability to accept my proposal RV prime, and if it is rejected, we just keep V as my sample. If I use this rule as my acceptance test ratio and just keep running, then this P here is my stationary distribution of Markov chain. Of course, if you replace P by your joint distribution, right, or the posterior distribution, it will be your target posterior. So this actually give you a general framework, like for any dynamic system, how do you construct Markov chain and follow what kind of rules can guarantee you to converge to your target posterior. Right? And now if we just apply this to the Hamiltonian system we constructed, right? We know that R is just negating the momentum, right? And for the acceptance test, first, according to the properties of Hamiltonian system, this determinant is always 1, right? Right. We just discussed like here, it's called a volume preservation, right? For any, no matter how long you evolve your system, your Jacobian of your state with respect to previous state, the determinant is always 1, right? So this guy is just 1, right? And this guy is just the joint probability of your state, right? At your proposal RV prime, but RV prime is just the Z and negative R, right? And this is actually to the exponential of the energy, right? And this energy, the kinetic energy, because we use the quadratic form, okay, actually negative R and R give you the same kinetic energy, doesn't change, right? And for this one is just exponential to the energy of H, Z and R. And this is of course ZT and RT, something like that, right? But we know that Hamiltonian system is energy conserved. It doesn't change the energy. So that means the energy at time t, energy at the beginning doesn't change. This probability, joint probability doesn't change. So this guy eventually is 1. So that means if you apply Hamiltonian system to generate sample proposal, the acceptance probability is simply 1, like Gibson. Okay, let's stop here today. And we put the link to the proof of this theorem. If you're interested in that, it is in my some academic brothers PhD thesis. It's not hard, but it's very interesting proof and give you a very broad general framework how to construct dynamic system-based Markov-Chain Monte Carlo algorithm. If you're interested, I do suggest you to take a look. And also, please try to apply this theorem to the Hamiltonian system and instantiate our discussion again. It will definitely strengthen your understanding of this. Okay, I'll see you on next Tuesday.